Okay, this is lecture 10 of basic calculus 1. If you recall, we had just discussed the concept of limit at a point, a real number c, and then in that connection we had left side limits, we have right side limits. Then we move to limits at infinity, that is x goes to infinity or x goes to minus infinity. And also we discussed how a limit of a function can become equal to infinity or minus infinity at a point c, or even when x goes to infinity or minus infinity. So, today we will be extending those notions and discuss the continuity of a function. So, continuity of a function, when we say continuous, in fact it says something like continuity over an interval. It is a process. So, continuous process means it continues throughout an interval of time. So, here we do not have time, we have a function which will be telling that it is continuous throughout an interval. But in mathematics there is another thing. Instead of just telling continuity over an interval, we will also be talking about continuity at a point. It looks a bit ridiculous linguistically. What is the meaning of continuity at a point? It should be over an interval. However, the negative concept of it, that it is not continuous at a point, is meaningful, and that is what something like continuity means. There is no break. So, you would say that a function is continuous if it is not having a break at that point. So, what is the meaning of not having a break? You have some look at the graph of a function. So, it grows. You say at this point, last one, there is a break. So, that means you cannot continue as you drew it. You may have to jump and do something like this or something this way. So, that is what we mean, that there is a break. So, this is what we are going to define, that a function is not having a break. So, you should understand what is the meaning of it is having a break. Let us look at this function which is drawn here. Its graph is given. It is defined over 0 to 4 and its values are given in graphical way. So, let us look at the point x equal to 1. Obviously, if we start drawing it, the values at 0 it is 1, from 1 it decreases to 1, then at 1 there is a jump. Instead of 0 it goes to 1 there, and f of 1 is also given as 1, it is not 0. That is what you see, it is an empty circle, a hollow circle, and on the top there is a solid circle. So, that means f of 1 equal to 1, not f of 1 equal to 0. So, there is a jump here. Now, when you see there is a jump, what is exactly happening? Let us try to connect with the definition of limit in the same style. So, suppose I choose my epsilon equal to half. So, see here there is a jump, the values of function values near 1. So, before this 1, if you take close to 1, it is looking near 1, and at 1 it is going equal to 1. So, near 1 it is 0, near 0, right? The functional values are near 0. So, the gap is 1 unit. Suppose I choose my epsilon to be half unit, say epsilon equal to half here. Then let me choose any delta I like, where from I will choose my x. That is, here the left side is we are concerned, not the right side. So, let us take the left neighborhood, which is x minus delta to 1 minus delta to 1, that is our neighborhood for any delta you take. Of course, the values should be inside the domain. Now, take any delta, if you take bigger delta does not matter, but values inside means it will come back to this point 0. So, delta can be maximum 1 to be meaningful here. Okay, take any delta. Now, in this neighborhood 1 minus delta to 1, I can always find a point x such that f of x and minus f of 1. So, this distance is bigger than half. This is what it says. Okay. So, that is the meaning of it is having a break there. It is having a break. That means I cannot make them as close as I want. There is always something, the functional values will be bigger than that. Difference between the functional values between f of 1 and some f of x is always bigger than this. So, I can never make them closer and closer by choosing my delta neighborhood. So, when you take the negation of it, that this does not happen, then what happens is, we have started with there exists one epsilon. So, we will say for every epsilon greater than 0, there exists a delta instead of for every delta now. Corresponding to each epsilon greater than 0, there is a delta, such that if I choose any point between x minus delta, that is 1 minus delta to 1, then difference between them is always less than epsilon. That will give us the function having no break at 1. Here it is having a break, so the opposite is happening. So, that is how it will be going towards the formal definition of continuity. But then as you remember, the formal definition of limit, we would say corresponding to each epsilon greater than 0, there exists a delta greater than 0, such that if you choose any point in the deleted neighborhood of delta neighborhood of that point C, any point x in the deleted delta neighborhood of C, the difference between the corresponding value f x and this L will be less than epsilon. That is the notion of limit. Now, instead of limit equal to L, we are comparing with f of x minus f of C mod. So, in the definition of limit, if we just take L equal to f of C, we would see that it is continuous at that point C. So, there is a connection between this and the notion of limit. So, exactly if you look at this function again, you see that the function is not continuous at 1, it is also not continuous at 2, there is again a jump, it is also not continuous at 4. So, this we are including at the end point, in the sense that we do not have f of 4 defined even. So, how do I say, how did I draw it including that point? I could not. So, it should be defined. Since it is not defined, we would say that it is not continuous at that point. So, these are of different kinds, at 1, at 2 and at 4, they are not, function is not continuous. At all other points it is continuous. Of what kind, what nature of this break or discontinuity is happening at these points? At 1, you can see that limit of f of x as x goes to 1 minus, that is from the left side, it exists and that is equal to 0, right. On the right side, you see that the limit of the function f of x as x goes to 1. So, the other curve is important here. So, you will find that its limit is 1. So, that means limit of f x at x equal to 1 does not exist, because they are having two different limits. So, that does not exist. It can also happen that one of the limits does not exist. Then also this condition that limit f x does not exist will hold. So, this is of one type, that at x equal to 1, limit of f x, x goes to 1 does not exist. What about 2? At 2 you find that left side limits, when x varies to the left of t, x remains to the left of 2, but near 2, you see that its limit is equal to 1, because all the values of f x lie near 1. On the right side again, that is also near 1. So, limit exists and it is equal to 2, right, but f of 2 is equal to 2. Yeah, its limit is not 2, its limit is 1. When it is left side, it remains near 1. When it is right side, it also remains near 1. So, limit of f x exists and it is equal to 1, whereas the functional value f of 2 is equal to 2. So, that means the limit exists, but it is not equal to the functional value f of 2. That is of different kind from the earlier, which is at x equal to 1. Then let us see at 4, at 4 it is simpler, it says that f of 4 is not defined. Of course, we can redefine it. Suppose we take a different function which is defined as fx for all the values given here, but at x equal to 4 its value is say 1, then it would become continuous at that right point. But here the notion of right side limit does not apply, because in the domain of definition of f we do not have any point to the right side of 4, only the left side is relevant here. So, as x goes to 4 minus, this limit exists and all those values of f x also lie near 1. That is why limit f x x goes to 4 minus exists and it is equal to 1, but f of 4 is not defined. So, had you defined f of 4 equal to 1, then it would have been continuous at that end point. So, you have to be cautious about the end points, because at those points one of the sides limit may not exist. It is not exactly may not exist, it is not relevant, right. Only one of them we can define and possibly talk about it. So, like in the point at the point 0, there is no notion of left side limit, it is only right side limit. Okay. But at that point f of 0 equal to 1 and the limit x goes to 0 plus is also equal to 1. So, you would say that it is continuous at 1, okay, continuous at 0, its value is 1, it is continuous at 0. So, that is why only these 3 points we see that there is a possibility of breaking. In fact, these 3 points only the function is discontinuous, not continuous. At all the other points it is continuous. So, this is how we will be connecting it with the limits. Let us give the formal definition first, what we discussed with the epsilon and delta. Suppose we have a function f from a subset of R, D is a subset of R, and we have a point C in D. We want to know what is the meaning of function being continuous at that point C. Remember, it does not have a break, that is what we have to say. So, we say that f x is continuous at C if what happens, correspond to each epsilon greater than 0, there exists one positive delta such that for all those x inside D for which the inequality x minus c mod less than delta is satisfied, that means for all x inside D intersection the delta neighborhood of C, for all those points we should have f x minus f c mod less than epsilon. In fact, this will be easier because we will be only considering D as intervals. So, for all those intervals, whenever D is an interval, you will see that D intersection C minus delta to C plus delta will also be a neighborhood, maybe only left neighborhood or maybe only right neighborhood. So, it will cover also the end points as we have discussed earlier. If it is an interior point, then you will get a neighborhood of course, but not this delta, maybe smaller delta, that is fine because we need only one such delta. So, that is how it will go. Now, you see that this definition is exactly same when instead of f c it was L in the definition of limit. So, a function f x is continuous at C at x equal to C, C should be in the domain whenever limit of f of x is equal to f of C. So, that includes many things, that the limit should exist, the function should be defined at C, of course C belongs to D, so it is defined. Then for the limit also there should be left side limit, there is a right side limit, they must be equal. But this is happening inside the for the interior points. If there are end points, then one side of the limit will not be relevant, so we will be considering the relevant ones. That limit should be equal to f of C. Okay, so that is how we will be connecting with the limit notion. So, we will fix some terminology. All that we have done is we have defined continuous at a point C. Now, if you take S is a subset of D having some of the points of D and you find that it is continuous at every point of that S, then you say that f is continuous on S. Now, in particular if S is equal to D, we will say f is continuous on D. So, again we will have a shortcut, we will not say continuous on D, we will just say that f x is continuous. taking care of the domain. So, that is how we will be starting from continuity at a point to function is continuous over the whole domain. So, in fact, this is the last one which is linguistically meaningful, not the first one. First one is mathematically meaningful, and we will continue with that definition. Okay. So, suppose in particular, because this is what we will be interested in, that the domain of the definition of the function is an interval, maybe a, b both closed, maybe one of them is excluded, so that semi open, or maybe both are excluded, so you get an open interval. This type of sets we will be considering as domain of our function. So, suppose at x equal to a, the set of points x in D with x minus a less than delta, which we are requiring in the definition, right. So, that will be looking like a b intersection a to a plus delta, because it is the end point a. The left side neighborhood is not contained inside our domain or inside the interval a b. So, when you consider this intersection, that D with the delta neighborhood of C, that would give only a to a plus delta, where that delta should be smaller than b minus a, right. You can start with any delta, but this will give rise to a new delta. You will always get one neighborhood of this type, a to a plus, let us say delta 1, where we can choose delta 1 to be smaller than delta appropriately, or even minimum less than minimum of delta and b minus a, that would give some neighborhood of this type. So, at the point left end point a, we have only the right side limit that is meaningful. Okay. So, that is what we say, only the right hand limit of f x at x equal to a is meaningful. Similarly, when x equal to b, so we have the interval now a b, and we are taking a neighborhood at b. So, it will be something like b minus delta to b plus delta. Then their intersection will be some interval of the type some b minus delta 1 to b. This delta may be bigger than delta 1, does not matter, the same way we will be choosing. So, this one will be meaningful, the left neighborhood. So, that means the left hand limit only will be meaningful. Now, these things will be helpful in connecting this continuity at a point with the notion of limit that we have done earlier. So, this is how we will be doing. Suppose f from a b interval to R is a function that is given, and C is an interior point of the domain. So, C belongs to the open interval a b. It is something like this, C is somewhere, some open interval, may be closer to a, may be closer, does not matter. Now, we say that this is continuous at C, f of x is continuous at C, if and only if limit of f x equal to f of C. Now, this limit really includes both left hand and right hand limits, because always you can find a neighborhood which is contained in the interval, closed interval a b. Now, this happens, suppose I write x equal to c plus h, where h can be positive or negative, right, c plus h, c minus h will be on the other side. Then I can express the same limit as limit of f of c plus h minus f of c, where h goes to 0. It is really x minus c which is our h. So, sometimes this last one is helpful in solving some problems. We will see where. So, now you see that f x is continuous at C, an interior point of a b, if and only if limit h goes to 0, f of c plus h minus f c equal to 0. Now, if it is an end point, say the left end point a, then as we have seen, only the right side limit is meaningful. So, we say that f x is continuous at a, if and only if limit f x, x goes to a plus equal to f of a, that c becomes a here. So, it is f of a, and that is again same thing as, because the left side limit is not meaningful, h cannot be negative. So, writing x as a plus h, we would see limit h goes to 0 plus a plus h minus a, x minus a, that is h. So, h goes to 0 plus of f of plus h minus f of a equal to 0. Okay. So, now when it is the right end point b, now again similarly the left side limit is meaningful, right side is not. So, we replace that limit f x goes to c with x goes to b minus. That is, it is continuous at the right endpoint b if limit f x goes to b minus equal to f of b. Now, again writing the same way as x equal to b plus h or b plus h, we would see that h should be negative. That is, limit h goes to 0 minus f of b plus h minus f b. But instead of that, we will say h equal to the positive side. So, we may write the left to b as a point in like b minus h. So, it would say limit h goes to 0 plus, both are writing now 0 plus, of f of b minus h minus f of b equal to 0. It is the left point minus the functional value. So, this is how we will be connecting the continuity at a point C, which is an interior point or a left end point or a right end point, with our limit notion. So, that we can use our limits, idea of limit, to decide whether some function is continuous or not. But sometimes the epsilon delta notion also helps, and specifically when you are going to use continuity, that becomes of immense help. Okay, so, what we see that if f is a function defined on the semi-open interval a b, where a is closed, b is open, it is continuous at x equal to b or not. We will say that this question does not arise, because b is not a point inside the domain. We can only think of points where it is continuous or not if that belongs to the domain. So, b does not belong to. So, you say that continuity of f x at x equal to b is not meaningful. We will not consider even the question, right? It is not a question. Okay. Similarly, if you have a open, b closed, then continuity at a will not be meaningful, right, because f of a is not defined. So, similarly for all these, if it is both open, then continuity at a, continuity at b does not arise, right. So, similarly a to infinity, infinity is not a point in real numbers, and it is also, that is why we are writing open. So, at infinity has no meaning, but at a has a meaning, it is the right side limit. Similarly, all these. So, these are just guiding lines to connect continuity with limit and how to carry over.